Now, let us quickly go through one example problem and let us see how the sections can be designed for both shear, torsion and bending. Now, this is an example, this is the same cross section that we have been using for both flexure and shear examples. It is a I section with flange widths of 500 mm, thickness of the flange is 200 mm, web width is 150 mm, and you see that we have 14 numbers of half inch strands, and the section we are designing is going to have a torsion of 75 kilonewton meter and a bending moment of 1000 kilonewton meter and a shear force of 350 kilonewton, right. Now, given concrete properties are characteristic strength of concrete is taken as 60 and FPU is 1860 and effective pre-stress is 1100 and effective pre-stressing force is 2000 kilonewton, and these are the concrete sectional properties. And here you see that I have taken a very high diameter, usually we do not provide it. Usually stirrup dia has to be less than 12 millimeter. Now, then why did I take 20 millimeter? Because we have already done the calculations and the shear demand is so high, if with the 2-leg stirrup, otherwise my spacing will become so less. So, because you see here, even though the torsion magnitude is 75, you will later see in the design that the stirrup requirements will become very high. So, one way to tackle is maybe I can increase the web width also, that also will help to an extent. But now let us say that, so usually we do not provide 20 mm, but if the demand is so high, then we have to specially order it and fabricate it and bend it and put it in the site. Okay. So, let us go to the design for torsion. Now, what is the effective depth? Overall depth minus clear cover minus diameter of the stirrup minus half the diameter of the longitudinal bar. So, if you substitute all of them, you get 954 millimeter. I am converting the torsion into an equivalent bending moment. You see, we got only 75 kilonewton meter in a torsion, and when I convert it, you will find that because the depth is so large, 1000 millimeter, and breadth I have to take width of the web, not the flange. So, you will find that 75 will be converted into much larger value of 284 kilonewton meter. You see here, only 75 kilonewton meter of torsion is getting manifested in the form of 284 kilonewton meter, which is roughly 4 times. So, that is the the torsion. So, torsion, when you convert it into an equivalent bending moment, the value will become very high. If one you have width is less. The one way I can reduce this MT is by increasing B. Increasing B will help me to reduce MT. But now that my section dimensions are fixed, I am going to go with whatever I have. Let us see what we have, what we get out of. So, the total bending moment what I need to design is 284 plus 1000, which is given, which is 1284 kilonewton meter. Now, you can use the approximate method that is given in the table 11, and for that you can go back and look at let us select 0.095. So, the stress ratio works out to be 1, and then FPU is 1618 megapascal, and then XC by D works out to be 0.195. Okay. So, this is the reinforcement index that I am choosing, right. So, XU is working out to be 186, then I am getting my moment resistance is 1970 kilonewton meter. Now, this is tension force Tp times the lever arm. So, we have studied in flexure. Okay. Now, from this table using approximate method, I can quickly calculate for any assumed AP what is the neutral axis depth. Once the neutral axis depth is known, then I can quickly calculate my moment resistance. So, that is what we have done, right. Now, how did we get the reinforcement index? The section already it is given 14 numbers of half inch strand, but if you do not do, you can assume values and then you can calculate to make sure that this value is higher than 1284 that what we have. Okay. So, that is how you design. Okay. So, mu is greater than me1. So, the section is adequate for resisting the applied moment. So, we have designed the flexure. What is that we have done? We have converted the torsion into an equivalent bending moment. We just designed it with that. Now, in addition to that, I am also going to provide 2 numbers of 12 mm diameter bar, longitudinal bar to hold the stirrups. Now, it is an I section. So, I need to put stirrups in the flange as well as in the webs. So, I need to put some longitudinal bar, non-pre-stressed longitudinal bar to hold the stirrups. Now, let us look at now what is the next step is to design for shear. Now, how do we do the design for shear? Now, the cable profile, last class also we have discussed, last part of the video. The cable profile is a parabolic, so I can convert this into this 4 delta x by L minus 4 into delta into x square by L square, where delta is the eccentricity at the center. So, E is the eccentricity at any section x that I can find out using this parabolic equation, right. Now, why is it we are doing calculation at x is equal to 0.2? We have seen that the width of the bearing is 0.4 meter. I am doing the shear demand calculations at the x is equal to 0.2, which is half the bearing width. So, at that location E is 0.02236 meter. So, if you substitute that to calculate your pure VC naught, first we need to find out VC naught and VCR, and VC naught is your web shear. This is web shear. We have seen that in the last class, last lecture, and there is also a vertical component due to pre-stress, which is PE into sin theta. So, if you substitute all these things, the theta works out to be, this is your equations for the cable profile, and then this is what we explained it in the previous thing also. The eccentricity at a distance x is equal to 0.2, we calculated it previously, and the slope of the cable profile, if you substitute it, the delta is 0.425, right, and if you put x is equal to 0.2, then you get your theta as 0.1103, and VPE component is going to be 220 kilonewton. It is the same thing that we did previously, right, and tensile strength of the concrete is assumed as 0.24 square root of FCK, which works out to be 1.85 megapascal, right. So, and FCP is PE by AC, which is 6.89 megapascal. So, you plug in all the values and get your VC naught, this plus this VPE, both are there. So, you get 592 kilonewton, and VCR is equation is this, like last lecture we have seen, and FPE by FP is 0.59. So, this is 0.59. Now, what is psi z is function of your percentage of steel, and PT works out to be 0.97, and then dt we have to take a higher value, we cannot take the lower value, or you take, if it is coming very low, then you take 0.8 H. So, your dt can never be taken less than 0.8 H, okay, that you keep it in mind. You cannot take a lower value, because I put some normal steel also. So, that works out to be 954. If you substitute that, and m naught is a decompression moment, again last lecture we have seen how to calculate that, and eccentricity we have already calculated it. At x is equal to 0.2, eccentricity works out to be 0.02236, right, or 22.36 millimeter. It is a small eccentricity, but we have to include that, and the FPT works out to be 7.52 megapascal, and if you substitute, your decompression moment is 425.85 kilonewton meter. So, if you substitute that, and for calculating now m naught we have calculated. Now, in that equation you see that we got this 1 minus 0.55 times that effective ratio, then 1.42 is your psi z, shear strength of the concrete, and 150 is your breadth of the web. This is your breadth of the web, this is your psi z or shear strength of the concrete, and this is your effective depth dt, right. This is your FPE by FPY ratio, and this is your additional component that we have, okay. So, you see here, this is, if you find that VCR in this case works out to be 286 kilonewton, which is a lower value, because for this problem, if you see the shear demand is low, TC, which is your pure torsional capacity when only torsion is acting, concrete capacity in torsion, and lambda p value that works out to be 1.54. So, when you substitute that, your concrete capacity in pure torsion is 39 kilonewton meter. Now, how much is it acting when it is acting along with shear? Tc into E by E plus C. So, this is some kind of a reduction factor that we have already discussed, and similarly you calculated Vc, and Vc1 when it is acting along with torsion is this again some kind of a reduction factor. So, you see if you put this as the value, E is equal to 75 by 350. So, that works out to be 0.75 is a torsion and shear is 350. So, if you take that ratio, it is working out to be 0.214 and EC is TC by VC, which is 0.133. So, TC1 works out to be 24. You see, in pure torsion we had 39 and this has reduced when it is acting along with shear, the concrete capacity in torsion has reduced from 39 to 24, right. Similarly, VC1 has reduced from 286 to 177. So, now ASV is greater of MT into SV. This is from amount of stirrups. There is a minimum reinforcement requirement that we need to satisfy. So, it should be greater than this and this. So, now let us look at what is the requirement that we are getting. So, if you assume spacing of 75 millimeter for a 20 mm diameter, ASV works out to be, now MT is 284, we have calculated that 284 into SV, which is 75, 1.5 and B1 is 112 and D1 is 916 and Fy is 415. See, again in stirrups for calculations, Fy cannot be greater than 415. Okay. Even if I am using 500 grade, my yield strength in my calculations I should use only 415 megapascal. So, this works out to be 334 millimeter square. And for shear, now again what is the additional stirrup requirement is V minus VC1 into SV by 0.87 D1 into Fy, that works out to be 40 millimeter square. And for torsion, it is T minus TC1 into SV divided by 0.87 into B1 into D1 into Fy. So, you substitute the number, you get your 104 mm square. Now, you add, this is basically AV plus 2 times AT. So, you see you get a requirement of 248 millimeter square. So, which is quite high. Now, again we have to check the spacing, it cannot be less than this 112 B1, this is nothing but your B1. The next one is your B1 plus D1 by 4, which is 257 or 300 mm. So, if you substitute the least one, that I need to take 112 is the spacing. Now, anyway we are assuming 75 millimeter, so which is okay. So, you see here, that is the reason. So, we are taking B1 as 112 and D1 as 916 and so on. So, this spacing is for the SV. Now, for flange, so whatever that we have provided is okay. Now, for the flange, horizontal shear stress that we have to calculate, again that we have discussed this in the last lecture as well. You take the area and maximum shear is going to be here. So, you take this area and you take about this axis. So, basically VQ by IB. Now, the thickness for this is going to be depth of the flange, which is 200 and Y is again is going to be 500 and your A1 is going to be half of your BF into DF. So, we did all those calculations and maximum shear stress works out to be 1.23 megapascal. So, if you substitute all of them, you get your horizontal shear force VF equal to 31 kilonewton. This is the same thing that we worked out in the previous example in shear. So, it is the same thing and the horizontal flange stirrup requirement will be VF divided by 0.87 into F5, which is 85 millimeter square. Then the spacing works out to be 385, but then again I have to satisfy some minimum spacing requirement as per the dimensions like last lecture we have seen. So, we can go ahead and put 10 mm dia stirrup at 375 center to center, right. So, finally, if you look at it, now again the depth has become more than 450 millimeter. So, I need to put some side face reinforcement, which is 0.1 into BW into DW by 100, 90 millimeter square. So, I am going to put some 2 numbers of 8 mm bar as a side face reinforcement at 300 mm center to center on both faces, and this is for flange. This is a very large diameter stirrup, 2 leg stirrup, because you have torsion, right. And strand for flexure 14 numbers, because this is at support. So, this is a location at support. Okay, this is at support. Okay, so you have 12 mm diameter long till bar again to hold the stirrup. So this is the final designed section. So this is for the overall section. So you have seen that even though the torsional moment was only 75 kilonewton meter, that get manifested in the form of a very high equivalent bending moment. Similarly, the shear demand also increased. That is the reason we are ending up with very high amount of stirrup that we need to be careful about. Okay. So let's summarize what we have discussed. We have discussed the different types of torsion, that is equilibrium torsion and compatibility torsion. We examined what is the effect of pre-stressing. We have seen that the pre-stressing increase the cracking torsional moment, and but however the ultimate strength, it does not really play a major role, right, of similar sections. So pre-stressing definitely helps in increasing the cracking torsional moment. And we analyze the section before and after cracking using thin wall tube theory and skew bending theory, and then we highlighted the key provisions from IS 1343, and we illustrated the design for pre-stressed concrete beam using combined action of shear and bending and torsion through a design example. Right. So with that, we are completing this module on torsion. Thank you. I look forward to seeing in the future modules. Thank you.